Okay, let's dive into this explainer. Today, we're doing something really cool. We are going to act as universal translators, decoding the absolute lowest levels of computer science to see how machines actually think. We spend our whole days interacting with glowing screens full of rich text, high-definition videos, and complex video games. But underneath all of that magic, there is a remarkably simple, rigidly logical secret code.
Think about it at the absolute microscopic level. Computers are literally just massive networks of tiny, simple switches. They don't understand letters or colors or sound, nothing like that. They only understand on as a 1 and off as a 0. A single 0 or 1 is called a bit. It is the fundamental, indivisible atom of all computing.
Now you might be wondering, that creates a massive translation problem, right? If a computer is really just a giant box of light switches flicking on and off, how in the world do we get from one solitary binary bit to writing an entire 500-character text document? How does a simple 0 or a 1 become an A or a B?
So here is how we're going to climb this mountain step by step today. First, we'll look at bits, bytes, and text. Second, the binary number system. Then, we'll tackle the negative problem, explore hexadecimal and conversions, and finally, look at floating point numbers and arrays.
Section 1. Bits, bytes, and text. This is where we build the Universal Translation Dictionary.
To solve that whole email problem we just talked about, computers group those tiny light switches into things called bytes, which are just sequences of 8 bits. And to actually make sense of them, early computing pioneers essentially wrote a universal translation dictionary. Notice how every single character on your keyboard, even the blank space, has a completely unique 7-bit ASCII code. This was developed way back in 1963. If you type a capital A, the computer stores it as the binary sequence 1000001, which equals 65 in decimal. Even just mashing the spacebar sends its own specific binary sequence. It's wild. But ASCII definitely had a limit. It only accounted for 128 characters, mostly just English letters and some basic symbols. As computing exploded globally, we obviously needed more. So we moved beyond ASCII to a new standard called Unicode. Unicode uses variable bit widths, which is a real game changer, because it gives us the power to represent over 100,000 unique characters. We're talking different global alphabets, complex symbols, and yeah, absolutely all the emojis you use on your phone every day.
Moving right along to Section 2, the binary number system, counting with 2 fingers.
So we know how computers store letters, but how do they actually do math using a system with only 2 digits? Well, humans have 10 fingers, so we naturally use a base 10 decimal system. We count 0 to 9, run out of digits, and then we carry a 1 to make 10, right? Binary counting works exactly the same way, but it's base 2. Just like you carry a 1 when you count past 9 and base 10, binary carries the 1 every single time it passes the number 1. So 0 is 0, 1 is 1, but 2? 2 is 1, 0. 3 is 1, 1, and 4 is 1, 0, 0.
You can count as high as you want in binary, as long as you just keep carrying that 1. But here is the critical problem. Unlike our own infinite imaginations, computers have a hard, physical limit on how many bits they can actually hold in their memory registers at one time. If you try to add numbers that exceed that physical bit limit, the leftmost carry bit literally just falls off the edge. Imagine adding 1 to the highest 4-bit number, which is 1111. The correct answer should be a 5-bit number, 10000. But if your machine only has 4 bits of space, that 5th bit absolutely vanishes into thin air, leaving you with 0000. This triggers a very dangerous system error known as overflow.
All right, Section 3, the negative problem, teaching a computer to subtract.
Okay, so we've learned how to add, but how on earth do we represent negative numbers without building entirely new, super expensive subtraction circuits into our machine? The brilliant solution to this is called 2's complement. It's a simple 2-step mathematical recipe where we use that leftmost bit as a sign indicator. To make a negative number, you just take the positive binary version, flip every single bit, so 0s become 1s and 1s become 0s, and then you just add 1. That's it. So positive 3 is 0011. Flip it to 1100, add 1, and boom, you get 1101, which the computer perfectly understands as negative 3. And this brilliantly illustrates why this trick is so widely used. By converting subtraction into addition, the computer can use the exact same hardware circuit to do both. If you want to calculate 5 minus 3, the computer just adds positive 5 and negative 3 together. The leftover carry bit overflows and is completely ignored, leaving us with 0010, which is exactly positive 2. We achieve subtraction purely through addition.
Which brings us to Section 4, hexadecimal and base conversions. This is essentially the programmer's shortcut.
By now, you're probably realizing that staring at giant walls of ones and zeros gets pretty exhausting for human programmers. Enter hexadecimal. Hexadecimal uses a base of 16. It counts from 0 to 9 normally, but then it borrows the letters A through F to represent 10 through 15. Because 16 is a perfect power of 2, exactly 4 binary digits neatly compress into just one single hexadecimal digit. It drastically shrinks down how we read and write binary code.
You actually see this compact shortcut all the time, especially in web design. Colors on a screen use 24 bits of data, 8 bits each for red, green, and blue. Writing out 24 ones and zeros is a total nightmare. Instead, those 24 bits of color data are beautifully compressed into just 6 hexadecimal characters. So, a code like FF000 instantly tells the computer to max out the red bits and completely turn off the green and blue bits. Fast and efficient.
Finally, Section 5, floating point numbers and arrays, measuring reality.
Let's step away from nice, clean, whole numbers for a second and tackle the much messier problem of fractions. Integers are great for counting distinct things, like exactly 42 cars or 0 pizzas, but we need what are called floating point numbers, because the real world isn't easily divided into perfect chunks. We need to measure continuous values, like temperatures, weights, or microscopic distances. The decimal point literally needs to float around to give us those hyper-precise measurements.
To store these massive or microscopic fractions, the computer relies on an IEEE standard that works a lot like scientific notation. It handles this by slicing a standard 32-bit value into 3 distinct parts. You get one single bit just for the positive or negative sign, 8 bits for the exponent, and then 23 bits for the actual fraction, which is also known as the mantissa.
But this system has a genuinely fascinating flaw. Because we only have a limited 32-bit bucket to hold our number, we sometimes just have to accept a loss of precision. Some numbers, like infinitely repeating fractions or irrational numbers like pi, literally cannot be perfectly represented by a computer. They run out of bits, meaning the computer is frequently making extremely close approximations rather than perfectly exact measurements.
Now, once we know how to store all these complex data types, whether they're text characters, integers, or those floating point approximations, we can group them together sequentially into memory structures called arrays. By lining data up side by side in memory, an array lets us organize and instantly access huge lists of information using just a simple numerical index.
And there you have it. You've officially cracked the foundational code of how computers think. You've seen how they translate tiny switches into characters, do math with carry bits, hack subtraction with 2's complement, and compress data with hex. But I want to leave you with a truly wild thought to chew on. If storing just one 32-bit floating point number is this incredibly intricate, how on earth do supercomputers orchestrate billions of these arrays, all constantly updating in parallel to simulate global weather patterns, physics, or even human intelligence? It's mind-blowing when you really think about it. That's the true magic of the machine. Thanks for joining me on this explainer. I'll catch you next time.